Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discuss about the Kc, the total Kc synthesis, Kc nucleus synthesis he carried out in 1992. That synthesis we have seen there is a structure number 3, which is a tetrasaccharide. How he is synthesized, the retrosynthetic analysis of that structure number 2. Structure number 3, as we know that structure number 3, and there we utilize the concept of retrosynthetic analysis, and as we know that retrosynthetic analysis means what? The process of breaking down the target molecule into convenient starting material by using functional group interconversion and disconnection is known as retrosynthetic analysis, and according to that he got the fragmentation and doing as a disconnection, and as we know that disconnection is an analytical operation which help us to reach the reactant starting from the target molecule is known as disconnection. So that type of the thing, and the important term generally we are using in the retrosynthetic analysis, like as a FGI, functional group interconversion, means one of the functional group is converted into another functional group, so that disconnection becomes as a possible, so is known as functional group interconversion, or in short we can call it as a FGI. So then after fragmentation and everything we have seen during that retrosynthetic, and here we are applying, we are using as a retrosynthetic application, actual application we are discussing over here. So far we have seen retrosynthetic analysis, and we try to synthesize some of the intermediate by taking the precursor as a structure number 7 we have considered. It is act as an precursor is nothing but as a starting material, which is a versatile, we can call it as a compound. From that compound we can achieve the target molecule, that is the structure number 3, remember over here. So that is the thing, and here the scheme number 4th we have discussed over here, and there are 2 noticeable features in the assembly of the monosaccharide blocks which have to be commented for the benefit of the practitioner. And first, the use of the thaliamido group C specific comments in box number 1, and second, the use of glycosyl fluorides, as we know that glycosyl fluorides for the construction of the glycosidic linkage, and the combination of CpZmCl2 AgClO4 as an promoter used here, and M is nothing but as a Zr means zirconium, or the HF means hafnium, is highly efficient for the activation of glycosyl fluorides, and zirconium system exhibit the most powerful reactivity. Now that and in this piece of work, the silver perchlorate has been replaced by silver triplet, that is the scheme number 5 is represented over here. And now let's start from the this scheme which I am going to show over here, that is let's see here how we can show that one. So let's start that scheme number 5 over here. Now the structure number 5 I am showing over here. This is a structure which I am going to represent over here, the 5 let's see, that is a glycosyl fluoride must be present at an anomeric center, and where the fluoride which I am showing over here, and then as we know that here is a OMP, that is a paramethoxyphenyl, and as we know that are the abbreviations generally used over there, and then here is a acetyl group at this position. All are the here OMB, that is a here is a paramethoxybenzene. This is a paramethoxyphenyl. P stand for phenyl, B stand for the benzyl, and as we know that the clear-cut difference between the phenyl means this ring is nothing but as this type of the ring here, and benzyl means what? Benzyl means this type of the here CH2, and this type of the this is a, and here phenyl means this pH only here. So remember the slight difference, the structural difference of these two terminologies. Now let me show over here, and when this glycosyl fluoride here is attached, what is that? That is a NPHTS, that is a N-thaliamido. This is a structure protecting group. All these groups are protected by using as a different protecting group over here, and this is nothing but as a generally this is a monosaccharide, and which is a glycosyl fluoride. Generally we are calling it in terms of the carbohydrate chemistry, and let's treat this compound with another monosaccharide unit, and which we have used previously. Here let us see here again, once again 1 MB, then here NPHTH, and at this position there will be OTB DPS, and at this position hydroxyl groups are there, so that it can be act as an acceptor conjugate. Glyco conjugate means what? That this is a glycosyl fluoride act as an donor, and this will be the glycoside act as an acceptor, and this they are going to form as a bond as a glycosidic, or that process is known as a glycosidation, and glycosidic linkage is formed or glycosidic bond is formed, and we are getting as a disaccharide over there. This is a structure number 5, and this will be the structure number 4, and when the structure number 5 combined with structure number 4, here we can write OMB, and when they combine together, that is A is a reagent, and that reagent, the reagent, what do you mean by the A reagent? What are the reagent? That we are going to see the name of those reagent detail separately after this what we can call it as this scheme is completed. After that we are going to see that A means what? Reagent. And as we know that these are the protected group. OMP means what? Paramethoxyphenyl. MB means what? Methoxybenzyl. Hydroxyl is kept here. TBDPS means what? Tertiary butyl diphenylsilyl. So that are the group attached over there, and you may get here as a disaccharide. And what is that? It is very simple to join this one, and now this is joint fluoride joined with this particularly, and we are going to get here the product. Now here this terminal OMB, and here it remains as it is NPHTH. This group remains as it is OTBDPS. We can write it down as it is here OMB. We can write it, and that is utilized for the formation of bond other group NPHTH, that also remains as it is. Then this one OMB also remains as it is. O-acetyl group also remains as it is. And then here is OMP, that also remains as it is. And this structure is nothing but as a structure number 10. Up to the structure number 5 we have seen in a scheme number 4 actually. And now when this compound, this is nothing but as a disaccharide once again, and this disaccharide further treated with the reagent number B. And what is that B? We will see later on after completion of this what we can call it as a scheme. So now here after addition of the B over here, what are the changes or occur there, how disaccharide, the purpose selectively we are deprotecting this group. So another part of the group, they are remains as it is, there is no change at all, only this one is converted into as a hydroxyl group. Everything is remains as it is, so you can show as it is here. So let's see here O, then like this. So this part remains as the OMP, and this one also NA, NPH, TH as it is, and this one also OT, B, D, PS, it is also as it is. Here OMP, it is also as it is. Now here NPH, TH, it is also as it is. This one also OMP as it is. This one also OMP as it is. But here is a hydroxyl group. Selectively we protected by using as a B reagent, and now this disaccharide further treated with the another this type of the what we can call it as a structure number 5, this one. Now here also use as a 5 by using this glycoside we will get as a disaccharide. Now we have deprotected at desired product, because we deprotected as a desired hydroxyl group, and for this one again we are going to treat with this structure number 5. And as we know that the structure number 5 is as it is, this is a fluoride here, and here NPH, TH we can write as it is here OMP, and here we can write O acetyl group, here we can write OMB, and this is a thing we got over here. And now after that addition of these two together in presence of C is a reagent, and that reagent we will learn separately, and by using the combination is very simple over here. Once again look at this and this group we are joining together, and you are going to get here is a product, this one O, this one, then O, this one. So simple. So let me make this one is a small so that we can write it as it here. Now look at this part, you can write it as it is OMP, and then here NPHTH as it is, then OTB DPS over there, and here OMP, here once again NPHTH, here also OMP. Now here we can write OMB, and here now once fluoride join, here NH, here we can write OMP, here O acetyl group, and here OMB, and this structure, this is a structure number which this is a structure number 10. Now this 11, this is a structure number 11, and now in combining these two we got as a structure number 12 over here. Look at that structure number 12, and that structure number 12 further treated with the reagent D. We applied over here D, and after the D, what we are going to, D is a deprotecting group, this one is get deprotected, and finally you are going to get this type of the structure over here O. Then it's so simple to draw this structure here. This is a trisaccharide, as we know that this one. Now everything is the same over here. This one OMP, then here you can write NPH, TH, here also OTB, DPS as it is here OMP. At this position NPH, TH, here is OMP, and it here once again OMP, MB. Now at this position once again NPH, TH, here you write it down OMP, here only the OMB. Now specifically we converted that acetyl group into as a hydroxyl, and we got this is a structure number 13, and this structure number 13 when we treat with the structure number 6 over here, structure number 6 as we know that, and this is a structure number 6 I am writing over here, fluoride, that is a glycosyl fluoride, which is a very high what we can call it as a here NPH, TH, here also we can write this one OTB, DMS, and here we can show as OMB, and at this position OMB, that are the group MB, all this. And when this structure number 6 and structure number 13 join together, the reagent used here will be the structure number will be E here, and we will get the structure number 3 once again over here. And structure number 3, which is that, as we know that here simply we can show this one. So here we are going to get this one. So here O, this one, then O, this O, and these are the compound O. And now here OMP, here you can write NPH, TH as it is, and here only OTB, DPS, and here OMB, here once again OMP, here you can write NPH, TH, here OMB, here we can write NPH, TH, then here once again OMP, here OMB, and here we can write OTB, DMS, once again NPH, TH, here OMB, and here also as OMB, and this is nothing but as a structure number 3 over here, and this is known as a scheme number 5, which is represented over here. And reagent and the condition, now I already told you that what are the reagent and the conditions are used there. So for A, that is a structure number 5, the reagent is a AgOTF, then CpZrCl2 2,6 di-tertiary butyl 4 methylene, what we can call it as a pyridine, MS4 angstrom, CH2Cl2, 0 to 25 degrees centigrade, and the yield is obtained near about as a 56%. And the reagent B used here K2CO3, that is a potassium carbonate, and THF used as a solvent, and this reaction carried out at 25 degrees centigrade, and methanol once again used as an what we can call it as a solvent over here for maybe. And then structure, then reagent number 6, C is nothing but as a it is used for 5 AgOTF CpZHFCl2 2,6 ditertiary butyl 4-methyl pyridine MS4A strong CH2Cl2 0 to 25 degrees centigrade, and the yield is obtained near about 60%. And the reagent number D, N2H4 ethanol ATOH, then pH 100 degrees centigrade, that reaction is carried out, and then acetic anhydride in presence of methanol and CH2Cl2 dichloromethane used as an solvent get 72% of the yield, and the finally E is the reagent used there, and that reagent will be AgOTF CpZ HFCl2 2,6 ditertiary butyl 4-methylene pyridine MS4 angstrom and CH2Cl2 0 to 25 degrees centigrade, 50% yield is obtained for this reaction. The block-wise synthesis selected here allows the transformation in due time of 3 thaliamido groups into 3 N-acetyl groups, C compound number 3, and of the last one into the required N-acetyl groups. The problem of differentiation of the one amino group among 4 is thus easily solved as illustrated in scheme number 6. And now the scheme number 6 is represented over here. Now let's see that scheme number 6, how we can get that type of the starting from the structure number 3, we will get the different type of the derivatives, and as we know that the derivatives are the exhibiting biological activity, and that's why we are studying that one. So let's see over here how this structure number 3, this is a structure number 3 when it is treated with the reagent A. Now as we know that reagent number A, when it is treated with this, we will get as a structure number 14 now. So structure number 14 will be like this, O, then here O, then we can show this way O, this one O, then this one. So here at the terminal anomeric carbon atom there will be a OMP, and then here you can remember here 3 here is a NH acetyl group, here maybe as a NH acetyl group, here also NH acetyl group, and at the final here also these 3 groups are there, and remaining one here OTBD, here OTBDPS, and here OMP, here also as a OMP, but here OTBDMS, and now here at this position there will be a MBO, and here also we can write OMB as it is, and here once again there are again NH, AC, all these are there. So this is a structure number 14, and now when this structure number 3 will be treated with reagent B, and we will get as a different type of the things over here. It will be treated with RCOOH, that is a B reagent. What do you get here? Acid will deprotect this, and finally you will be getting as a structure the all the structures is same over here. We can represent once again O, this one, O, this one, then O, this one as it is, and finally this O, MP, then all other part O, T, B, D, P, S, then NH, there will be NH acetyl group, here also as a NH acetyl group, here NH acetyl group, but here NH, then this one C double bond O, then double bond, then this one, yes, this one, 1, 2, then 1, 2, then this one, once again 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 and 6. This will be the structure number 15 over here. Here you can write as it is OMP, here also as OMP, and here only O, TB, D, MS, and here remains as it is O, MB and O, MB. That is the structure number 15 which we have seen right now over here. And then once again, if you treat with the reagent number C, what do you get over here? And that is shown or the represented over here. In a C also same, only go on changing, you are going to get as a structure. Now I am only changing over here. Here we will get as a structure 3 as it is, but here is a C. When you add as a C over here, so here the changes, now here remains as NH, only I am going to make a correction over here only. Here is a C now, and we are going to get this. Everything is the same, only change is here. Instead of this, here we are going to get as a acetyl group, and rest of the thing remains as it is. That is the structure number 16. Now let us look at as a last one is a D over here, and once you take as a last one is a D, and after the D, everything is the same, only what is that changes are there here. So here only the changes here becomes OACT, and this is a slightly difference OMP. Here only here is a change, slightly change over there SO3 Na, that the changes, and that's become as a structure number 70, and which is represented in the scheme 6. And then E2 nod cofactor 1, so nod factor 1, that is a reagent, you can remember N2H4 ETOH 100%, and there 100 degrees centigrade you will get as 87% yield. Then B RCOH maybe as acid, 3 equivalent will get as a 2-chloro 1-methyl pyridinium iodide, ET thrice-N, then CS3CN 25 degrees centigrade, 72% yield is obtained. Then PPTS, then paratoluene sulfonic chloride ethanol 25 degrees centigrade, then acetic anhydride ET thrice DM AP, this one CS2Cl2 25 degrees centigrade, and 72% yield is obtained. Then TBAF, THF, then pyridine in presence of heated at 25 degrees centigrade, and we will get as 85% yield. Then CAN, methyl cyanide water 25 degrees centigrade 3. So final comments, an interesting feature of the Nicholas strategy is the judicious choice of 3 different protecting groups for the primary alcohol position, which on one hand withstand the glycosylation condition, and on the other hand can be sequentially removed. Such a nicely tuned strategy indeed allows the only synthetic assays described so far to the acylated node factor 2 weaker points are the moderate yield from the use of the fluoride glycosylation method and the rather low yield of the simultaneous removal of MB and MP protecting groups 1 complex molecules. So I think with this we have completed all the syllabus of the carbohydrate chemistry, and with this I wish the best of luck for your exam, and I think with this let us stop today here. So in the next lecture or in a next term we will see the semester number 4, that is again once we will meet for course number I think CCTP 10, that is a 450, which is a chemistry of natural product. Till then, have a nice day. Thank you.